So, welcome to this course on linear algebra and the lectures on linear algebra. I want to deduce so-called isomorphism theorems from the last theorem which I have proved. Last time I proved a theorem on homomorphisms. So, let me induce homomorphisms. Let me recall that because I want to deduce consequences from this theorem. So, recall that. Call the last theorem we proved, that was the following. Let f from V to V prime be a K-linear map. Of K vector spaces. And another linear map, and another one G from V to V bar, another K-linear map. I will try to draw a diagram in this corner. So, f is from V to V prime and G is from V to V bar. We assume with kernel of G is contained in kernel of F, and assume and G is surjective. Sometimes surjectivity I will also denote by putting a two arrowheads. That means the map is surjective. Then this is given. Then there exists a unique K-linear map which I will denote F bar from V bar to V prime. So, in the diagram this map, this dotted map exists, that is F bar we are denoting. Unique also, unique is usually denoted by this exclamation mark symbol with, if I go from V to V prime by F, that is one way, or I can go also first go by G from V to V bar and then follow it by F bar, that should be the same. So, G compose F bar. This equation is also usually saying that this diagram is commutative. The commutativity of the diagram is indicated by this circular arrow. So, that is, this is a commutative diagram. And the proof was very easy. Proof was just defining F bar, which is dictated by this demand. So, define F bar by take any element in V bar. So, F of V bar, V bar. So, take any element V bar in capital V bar, and because this map is surjective, V bar has to be of the form G of V for some V in V, and define this to be, because of this, define it to be Fx. Now, the only thing we need to check here is this definition does not depend on the pre-image of, oh, this is V, not X. This is V. This definition does not depend on V, which is the pre-image of V bar under G. So, that is the only thing. So, V this is well defined, that is one has to check, and then the demand is automatically satisfied by, we have defined it like that. Okay. Moreover, in this there was another part. So, moreover, it says what is the image of this new map F bar. Image of F bar is same as image of F, and kernel of F bar is same thing as image of the kernel of F under G, G of kernel F. These two equalities are merely verifications. You take any element here, put it is here, and conversely similarly for this. So, this was the last theorem, and I want to use this theorem to deduce now some more assertions which will be very useful for us. Okay. So, the first one, now this is usually known as isomorphism theorem. So, from a given linear map we want to get an isomorphism. So, let F from V to V prime be a k-linear map of k vector spaces. Then F induces an isomorphism which will be denoted by F bar, that is from V modulo kernel of F to image of F. Remember, we have defined a quotient space of V modulo a subspace. Kernel is a subspace of V and this image is a subspace of V prime. So, we have gone mod V mod the kernel. So, the this is an isomorphism, and what is the, how I apply the homomorphism theorem? We have given F, that is from V to V prime, this is we have given, but actually the image of this F really goes inside the image. By definition, this is any V goes to, this is any V goes to F of V, but F of V is already in the image. So, therefore, it is indeed F, you can think of a map from here to here. So, I will again denote it by F only, and there is a natural map here pi. This is a natural surjective map. This is any V here goes to V bar. V bar is now by definition, this we are denoting by V plus kernel F, or this is also, because this we are denoting this map as pi, this also we are denoting by pi of V. So, we have this map pi, and we have seen that pi map has kernel of F and it is surjective, pi is surjective. So, our just theorem what we have recalled, that says that I definitely have a map here, and that map I call it F bar, this is F bar, and I want to check that that map is a bijection, it's k linear is fine. I want to check that the map f bar induced by f is bijective. But we have noted in earlier theorem that image of this f bar is same as image of f. So, we have noted above that under these circumstances image of f bar is image of f, but image of f is whole thing here. So, therefore, f bar is surjective. We have also noted what happens to the kernel of f bar. Kernel of f bar is pi of the kernel of f, but pi of kernel of f is 0 element here. This is pi of 0, which is 0. So, we have checked that, therefore, this means f is injective. So, that proves f is bijective. So, from a given K-linear map we can get an isomorphism by going mod kernel and the image is the image of f. So, this is called an isomorphism theorem. And if you say from this now, the immediate corollary is we can deduce immediately we note what we have proved earlier, the rank theorem. So, what was the rank theorem? V finite dimensional over K, and f is a linear map from V to somewhere, V to V prime, K linear map. Then dimension of V equal to dimension of the kernel of f plus dimension of the image of f, and this we call it rank of f. So, to prove this, so by isomorphism theorem we know that this f will induce a map isomorphism f bar will be from V mod kernel f to the image f. This is a pi map here, natural canonical surjection, and f is defined, this diagram is commutative. So, in particular dimension of the quotient space equal to dimension of the image, because it is an isomorphism. So, dimension of the quotient space V by kernel f is therefore equal to dimension of the image. But dimension of the quotient space we know, it is dimension of the big space minus dimension of the kernel. And therefore, we get this formula. So, the rank theorem is trivial if you prove the isomorphism theorem. Okay. Also, we can deduce the dimension formula easily now. Okay. So note okay. So let me make it clear. So either use rank theorem to prove this formula or prove this formula to use a rank theorem. It depends what one assumes and what one proves. Okay. So thing to note is, if you have a quotient space V by U, the quotient space of V by subspace U, then dimension of the quotient space is the dimension U, dimension V minus dimension U. And remember, this we have called it a codimension of U in V. Actually, we can also say something about a basis. So, more generally, the residue classes, remember the images of the classes here are, we are referring them to as residue classes. They are the cosets of U in V. Residue classes xi bar in V by U form. So, these are the residue classes of vectors xi I in I V in V. So, we have here we have xi's and we have a natural map, pi map, that goes to V by U. This map is surjective, we know, and these xi's go to xi bar here, or we are also denoting by pi of xi, and any element of V by U is coming from somebody from pi. These residue classes form a k basis of V by U if and only if the xi I in I form a basis of a complement of U. So, that simply means, along with U, these guys form a basis of V. That means V is U direct sum k xi, and this is also direct sum. This is a complement. This is a complement of U. This is a complement of U. So, in particular, you get this formula again, because we know this is a basis. So, this, if you count them, if you, in a finite dimensional case, these are finitely many, and then that will give you this codimension. Okay. So, okay. So, in the new, in this codimension notation, rank f, rank of a map is codimension of the kernel. So, when f is a map from V to V prime. Okay, now I want to introduce a new vector space here. Out of f we get it. So, suppose f is a k linear map from V to V prime. Then what we know that we have two subspaces attached to f. One is the kernel f and then the other is image f. This is a subspace here, this is a subspace here, and we have gone mod this and found a codimension of this and this. So, we could do the same thing here. So, the quotient space V prime by image f, this is called the co-kernel of f, denoted by Coker. Is called the co-kernel of f. So, this measures how far f is from surjective. If you remember, this kernel measures the injectivity of f. Kernel is 0 if and only if f is injective. So, kernel f is 0 if and only if f is injective. This we have seen earlier. So, this subspace measures how far f is from injectivity. If it is 0, it is injective. If it is one dimensional, then it is close to injective, not injective but close to injective. The more the dimension, that more the away f is from injectiveness. Similarly, this co-kernel measures surjectivity of f. So, co-kernel f is 0 if and only if f is surjective. This is very easy because co-kernel 0 means, so this is equivalent to saying V prime by image f prime is 0, 0 space. This is 0 vector space means V prime has to be equal to image of f, but this is precisely surjectivity. Okay. So, with this I want to stop this topic quotient spaces, and now I will go on to matrices. So, now it is a big topic, it will go on for several lectures. I will call this section as matrices. And I will divide this big section into 3 sections. First of all the motivation to do matrices will come from linear maps. So, first I will study the matrix of a linear map, K linear map. Then I will study rank of matrices. Then I will study elementary matrices. This is the topic. These are the 3 topics we will mainly. So, matrices they provide a simple and clear way for mathematical computation. Of linear maps. So, first, before actually defining formally what a matrix is, I would like to start with a linear map. So let V W are K vector spaces and F is a linear map from V to W, K linear. To start with, I do not want to assume they are finite dimensional, but eventually I will assume they are finite dimensional. Okay. And we have seen that if I have a basis V, now I have to write basis V, I will write underlying V, and this I will denote Vi. I will denote by round bracket. So, this also thereby eventually when I assume I the finite set, I want to give the order to that finite set. So, which element come first, which element come later, and so on. For that reason, I am, instead of denoting by curly bracket where usually the set is denoted by, I want to denote it by tuple. And similarly, W, underlying W is, no, let me change this I to J. So, this is Vj, J in J, and Wi, I in I. So, I and J are index sets. Eventually, we will settle down to where I equal to 1 to m, that is this set. This, remember, this is the notation from 1 to m, and J is 1 to n. This is what we will do it eventually, but instead of writing this, I will keep writing I and J. So, we have a basis, and then we have noted that f is uniquely determined. F is uniquely determined by its values on a basis of, that means f is uniquely determined by this f of Vj, J in J. So, for this reason, I am going to write these vectors, they are vectors in W now, these are in W. So, I want to write them by using this basis W of W, these are K bases of V and W respectively. Okay, so what do we do? For each J in J, we write f of Vj. F of Vj, we know it is in W, therefore, it is a linear combination in Wi's. So, there are some coefficients, those coefficients will depend on the J also. So, Aij, Wi, I and I, where these Aij's are, what is varying is I is varying, J is fixed. So, this is I in I, and this is in K power round bracket I. I hope we remember this notation K round bracket I. Therefore, these images, these f of Vj's are actually determined by these coefficients, because we know the coefficients are unique, because Wi is a basis. So, these images, these images are uniquely determined by the coefficient systems, coefficient system. So, that I am going to denote by MF. But to remember that I got this is coefficient system is Aij. In this, I is varying in I and J is varying in J, and more actually, because these are only finitely many. In each, if you fix J in J, there are finitely many of them are non-zero. So, what is MF? So, this is by definition it depends on the basis V and W. So, M suffix I have to write V and W in the notation V W of F is this, and where is this? This is actually in k power I cross j. Think of it as a function from I cross j to k, a tuple I comma j goes to Aij, and this is called the matrix of F with respect to the basis V and W respectively. It is the rows are numbered by I and the columns are numbered by j. So, if in case if I is not finite, I j not finite, you remember this is this condition that say that if you fix j, that means if you fix any column, it has only finitely many non-zero entries. But this I am not going to do it for infinite, I will assume I and j are finite soon. So, this is the matrix which we get out of F, and if you know this matrix, F is uniquely determined. Okay, so now let us formally define what a matrix is, and that will match with this definition. So, definition: this, to understand a linear map, we got these coefficients and we put them in that form, and that actually gives a clue what to define. So, let us assume now onwards it is not really necessary. So, let K be a field, and I and j are two index sets. So, 1, the K vector space k power I cross j. We have seen k power any set is a vector space. In particular, k power this I cross j is a vector space. This vector space is called the space of I cross j matrices over K, or also with entries or coefficients in the field K. And its elements are called matrices. Its elements are called I cross j matrices over K. Okay. So, therefore, in what we have defined above is that is really the matrix. So, MF, M, V is on the top because we go from V to W. V to W, F, this is the matrix Aij, I in I, J in J, and V is a basis Vi, Vj, and W is a basis Wi. This is a basis of V, this is a basis of W, and with respect to these two bases we have defined the matrix of F with respect to these two bases. And thing to how they are remembered is F of Vj for each j in J, F of Vj is summation Aij Wi, I in I, Aij are in k power, this is varying, I is varying, k power round bracket I. So this is how one should remember F.